So, for all these last few lectures talking about gases, we're assuming they're very, very small particles and don't interact with each other much as they collide. As a matter of fact, infinitely small and no interactions. But you know what? That's not always true, especially when the conditions of pressure and or temperature grow very, very extreme. So PV equals nRT. So if I divide both sides by nRT, I get PV over nRT equals 1. Or in other words, this line right here in the middle describes an ideal gas. Or you could say an ideal gas is one that behaves such that PV equals nRT, or the ratio of PV to nRT equals 1. But you see, as I um, increase the pressure from, say, 1 atmosphere right down here in the very first parts of the x-axis here, to 200 and 400 and 600, and oh my goodness, the atmospheres are huge up here. As the pressures grow larger, it seems that the heavier gases, carbon dioxide and N2 would be fairly heavy. This is only 17, no, 12, 16 grams per mole, 28 grams per mole. The larger gases often will deviate from PV equals nRT at greater pressures. H2 is a very light gas. It still deviates from PV equals nRT at great pressures, but maybe not quite so much. But almost any gas, when you jack the pressure up hugely, it doesn't behave according to PV equals nRT anymore. It may even liquefy. So at big pressures, the gases don't behave like they normally do. But we normally deal with gases in room temperature, room pressure, and so we will often, as a majority of the cases, work with PV equals nRT as a matter of fact, as a matter of stoichiometry and such. Here we see that the colder gases also deviate quite a bit from PV equals nRT at larger pressures. Why would that be? Why would a warmer gas deviate less from PV equals nRT at hugely increased pressures? Well, if you think back to how I began this video, I said we assume that these gas particles are very, very, very small, which is an okay assumption for at some point, except for the last slide. The large particles actually show that they don't act as point particles, but also they don't interact with each other much as they collide. That's an assumption. But as we see here, it's a bad assumption if the gas is cold. If the gas is cold, it slows the particles down and in a sense gives them time to interact and react and push and pull on each other. So colder gases at huge pressures deviate a lot, but warmer temperatures at high pressures deviate, but not as much as the colder ones. Maybe because they're moving faster and they don't get the time to interact, and they still behave somewhat ideally in the sense that they bounce off each other perfectly well, ricochet. Here's some cartoon particles interacting with the walls of a container. So for ideal gases, we assume they have very little interaction with each other on the walls of the container. But for large pressures, where the particles become closer together and they may or may not interact with each other, that's when we start to see some non-ideal behavior. Compact them too much or make them very, very cold, they might start to interact with each other. So is it safe to assume that the particles in a gas are infinitely small points and do not push or pull on each other between collisions? And you see the answer, almost always yes, in the real normal situations. But as soon as I start to jack up the pressures and or temperatures, watch out. There's an empirically arrived at equation or an adjustment to PV equals nRT. I honestly don't believe I'd ever ask you to use it, but I want to show it to you anyway just to torture you. PV equals nRT. So P may have to be adjusted if the particles start to interact and be sticky, like interparticle forces, and the volume may have to be adjusted if the particles are larger and larger and larger. So this is the not infinitely small adjustment, and this is the no interaction adjustment. These constants A and B, well, N is just the number of particles and B is the volume. These constants, little a and little b, depend on the gas. They may also depend a little bit on the conditions, but we're going to assume they don't. So if I had which of these gases will vary the greatest from ideal, so this is an adjustment to the pressure, this is an adjustment to the volume. Both of those adjustments are greater if the constants are greater. So is there a gas on this chart that has a large A and a relatively large A and a relatively large B? How about, chlorine, look at that, it's up to 7. And then the B constant is 0.05, which is larger or comparable to many of the others constants. So I'm going to go chlorine gas. Probably quite a bit of interaction, and not infinitely small either, for sure. They're larger particles. Oh, that's it. Yay, into another video. Go have a refreshing beverage.